Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through everything you need to know for the upcoming test. So all of the topics covered are listed here. The blue ones obviously indices and exponentials, the black ones sequences and series. So I'll go through each of these. Let's start at the top with index laws. So I've written all of the index laws you need to know on the left-hand side for you. I won't go through them individually because you've done them to death since year 9. I put this one here in a different color though. This is the one that's probably new to you this year. So you need to be able to simplify expressions like these requiring multiple index laws. So let's look at this first one here. So it actually uses a few different index laws. So firstly, we have a product in the brackets. So we're going to use this index law here. Number 4 basically says if you have something in brackets raised to a power, you raise everything in the brackets to that power. So I'm going to start by raising minus 3 to the power of 4. Now make sure you put it in your calculator like this. Whenever you're substituting a negative, you need brackets around it. Because minus 3 to the power of 4 actually gives you a positive number, 81. Now we also need to raise a squared to the power of 4. So to do that, we're going to use index law 3, the power to a power rule, which says keep the same base and multiply the powers. B to the power of 3 to the power of 4, keep the same base and multiply the powers. And then we're done. So this next one here is actually quite tricky. It requires the index laws from 1 to 5 and also 7. So let's start with this fraction here. So index law 5 says when we raise a fraction to a power, just raise the top to the power and the bottom to that power. So that's what we're going to do here. So we're going to raise the top to the power. So to raise 2x squared to the power of 4, we need to use the index law we just used here. You raise everything to that power. So I raise 2 to the power of 4, and then I'm going to raise x squared to the power of 4 using power to a power rule. So keep the same base and multiply the powers. So similarly for the bottom, I go 3 to the power of 4 and y cubed to the power of 4. Now here we have a negative power. So this rule here says that if you're raising something to a negative power, you basically just flip the fraction and write it with a positive power. And that's exactly what we're going to do here. I'm going to leave the division symbol for now and flip the fraction and change the power from a negative to a positive. So now I'm going to raise top to the power and then bottom to the power. So this is what I got from raising this fraction to the power of 3. So now what I'm going to do is I'm going to flip this second fraction and make it a times. So now that I have two fractions multiplied together, I can just multiply the tops and multiply the bottoms. To save me a bit of work though, I might do a bit of cancelling. 16 goes into itself once and goes into 5, 12, 32 times. 81 goes into itself once and goes into 729 9 times. Now to deal with these indices, I can use this law here where I'm dividing. So x to the power of 8 divide x to the power of 3 gives me x to the power of 5. So on top I have a 9 and now I have x to the power of 5. So then I can do the same for the y's. Y to the power of 15 divide y to the power of 12 just gives me y to the power of 3. And then on the bottom, I'm just left with 32. And that's my final answer. Can't be simplified any further. So we might get a question like this where we're asked to evaluate, which means give the value of. So our answer should be a number. So to do this, I'm going to use index law 6, which I haven't used yet. So anything non-zero to the power of 0 is 1. So 1 to the power of 0 is 1. 2 to the power of 0 is 1. Minus 12 to the power of 0 is also 1. So these two expressions here, these two terms look very similar, but they're slightly different. This one is not raising 4 to the power of 0. So this here is 4 times 1, which is 4. This, in this term here, the whole thing's being raised to the power of 0. So 4z all raised to the power of 0 is 1, assuming z's not 0. So this will be 4 plus 1, which gives 5. So let's look at index law 8, which you may not have learned until this year. So it says if you're raising a base to a fractional power, the denominator of the fraction tells you which root to take, and then the numerator of the fraction tells you the power to take. So what that means is if I have something like x to the power of 5 over 7, the bottom number of the fraction 7, so that means I'm taking the 7th root, and the top number's 5, so it's x to the power of 5. So here we're going to go the other way. We're going to start with a radical and write it with a fractional power. So we're going to have the same base x. So this number outside telling us which root to take, that goes on the bottom of the fraction, and the power of x goes on top. So it's x to the power of 4 over 9. So this one here is very similar. We have the 3, so we're just going to write that as it is, that 3 on top. Now we have the cubed root of x to the power of 8. So that will be x to the power goes on top, and which root we're taking goes on the bottom. Now, because this radical was on the bottom of the fraction, the power is going to be negative. That's using our rule here. So these two are the same. So we can combine fractional powers with the other index laws. So let's do that here. We've got 2x times root x to the power of 3. So note, root x is x to the power of half. So this is the same as 2x times x to the power of a half, all raised to the power of 3. Now, to simplify x times x to the power of half, we can just use this basic rule here. Keep the same base and add the powers. So that's going to be 2. We've got x to the power of 1. X and x to the power of 1 are the same. So we're going to keep the same base and add the powers. Okay, so now to simplify this, we're going to use the index law we used at the start. So if you have a product in the brackets raised to a power, you just raise each thing in the brackets to that power. So to simplify this, I'm going to raise 2 to the power of 3, and then x to the power of 3 over 2 to the power of 3. So keep the same base. And then 3 over 2 times 3 gives me 9 over 2, and I'm done. Alright, that's all for the crash course in index laws. Let's now move on to scientific notation. So scientific notation is when you have really large numbers or really small numbers and you want to write them in a more convenient way. So this is how you write in proper scientific notation. It needs to be some number times 10 to the power of something. This is always a whole number, can be positive or negative, and this can be a decimal, and it's got to be between 1 and 10. So this is really easy to do. All we do is start with the decimal point, and we keep moving the decimal point until the number's between 1 and 10. So if I move the decimal point here, this number will become between 1 and 10. So then it will be 2.74362521. So that's writing all the digits. So that's what goes in the first box. Now what goes in the second box is the number of places I move the decimal point. So here I move the decimal point 3, 6, 9, 10 spots. So it will be 10 to the power of 10. So this isn't really that convenient because this has heaps of digits. So you'll often be asked to write in scientific notation to a specified number of significant figures. So significant figures can be a bit tricky when we're dealing with 0. You see, any number that's not 0 is counted as a significant figure. All of these numbers here are significant digits. So if I wanted to write this to say 3 significant figures, the 2 counts as a significant figure, so does 7, so does 4. It would just be 2.74 times 10 to the power of 10. So this is an approximation to 3 significant figures. So let's try this one here. So this, unlike this one, which was a really large number, this is a really small number. But the process for writing in scientific notation is the same. We move the decimal point until the number's between 1 and 10. So we get 3.109 times 10, and we moved the decimal point 1, 2, 3, 4, 5 spots. So we put a 5 up here. Now you need to remember, if the number was really small, if it was less than 1, the power is actually a negative whole number. It's negative because we moved the decimal point to the right. So now this number here actually has 4 significant figures, 1, 2, 3, 4. Significant figures are tricky when you deal with 0. You see, all these zeros at the start of the number are not significant. We don't count any of them as significant digits. This 0 does count as significant because it's between non-zero digits. Confused? I get that it is confusing. So zeros don't count as significant at the start of the number, but they do count as significant between 2 non-zero digits. So that's why this has 1, 2, 3, 4 significant figures. None of these were significant digits. So if I were asked to round this to 3 significant figures, well, this is a significant figure, so is this, and so is this. This one here is 5 or more, so just like with rounding, I raise the score. 5 or more raise the score, so I'm going to raise the third significant digit by 1, and I'm just going to keep the 10 to the minus 5. So this is the answer to 1, 2, 3 significant digits. So let's try this worded question here. Number of bacteria in a colony is this, really large number, doubles every 2 days. How many bacteria will be there in 2 weeks? And we're going to write in scientific notation. No way you'd ever get a colony of bacteria with this many in. This is just such a large number. I just purposely put a large number because you can't put this on your calculator. Well, most calculators, this number would be too big. So it's going to double every 2 days for 2 weeks. So it's going to double 7 times because there are 7 lots of 2 days in 2 weeks. So the number of bacteria, so this is what we started with, 3.25 times 10 to the power of 125. So if it's going to double 7 times, we're going to times it by 2 7 times. So this number here is not incorrect scientific notation. 3.25 times 128 is definitely not between 1 and 10, which it was required to be. See, 3.25 times 2 to the power of 7 actually gives us 416. So 416 times 10 to the power of 125, to put it in scientific notation, this needs to be a number between 1 and 10. So how am I going to fix that up? I can't just put this on my calculator because the number's too big. What I'm going to do is write this number in scientific notation. So 416 in scientific notation is 4.16 times 10 to the power of 2. It's to the power of 2 because I would have started with a decimal point here and moved 2 spots. I still have the 10 to the power of 125. So these two are the exact same number. So 10 squared times 10 to the power of 125, just using our index law, we're going to leave the 4.16 alone, keep the same base, and add the powers. Now this number is in correct scientific notation because we've got a number between 1 and 10 times 10 to the power of a whole number. All right, let's now look at graphing some exponential functions. So exponential functions are graphs of the form y equals a to the power of x plus b plus c. The idea here is that the x is part of the power. So let's go ahead and look at graphing this one here. See, all exponential functions, they sort of have the same general shape. So they look like this. That's if a is greater than 1. So the number here greater than 1. That's an increasing function. Or they sort of go the other way. If a is less than 1, then it's a decreasing function. So because here our a value is 2, that means that this will be an increasing function and look like this. So this constant by itself, that actually tells you the asymptote. So this would have an asymptote at y equals 3. So why would this have an asymptote? Well, this is because this thing here, 2 to the power of x minus 1, can never equal 0. It can never be less than 0. So y can't be 0 plus 3, which is equal to 3. See, if you raise 2 to any power, you always get a positive number. Remember, even if you raise it to a negative power, the answer is positive. Like 2 to the power of minus 3 is 1 over 2 cubed, or 0.25. If you raise 2 to a negative power, you still get a positive answer. So this always has to be at least a little bit more than 3. So as x gets more and more negative, what's going to happen is this is going to get closer and closer to, but never actually hit the asymptote. So what we can do is just add in a few more points and then join it up in a curve that looks like this. So what would be the y-intercept? Well, the y-intercept always occurs when x equals 0. So if x equals 0, y would be 2 to the power of 0 minus 1 plus 3. 2 to the power of minus 1 is a half. So the y-intercept would be 3 and a half. So it would be like up here. So you can add in a few more points if you want as well. If x was equal to 1, y would be 2 to the power of 1 minus 1, 2 to the power of 0, plus 3, which is equal to 4. If x is equal to 2, then y would be 2 to the power of 1 plus 3, which is 5. And then so on. If x was equal to 3, y would be equal to 7. And if x was equal to 4, y would be equal to 11. Just substituting into the equation. So then our graph is just going to look like this, without too much fuss. All right, let's look at this graph here. So now we're going to do the opposite. We're going to find the equation of this graph. So we know that an exponential function has this form. I just need to find a, b, and c. So c is the easiest to find. The constant by itself, as it was in this example, that is the asymptote. So the asymptote here, you can see, is at y equals minus 3. So in this case, this means c is minus 3, because that's where the asymptote was. So what we know so far is that the equation of this graph is going to be y equals a to the power of x plus b minus 3. So what we're going to do, to find a and b, we need 2 points that it goes through. And of course, we want to pick points that are easy to substitute in and easy to see. So how about we pick this point here, which is 0, 0, and also this point here, which is 1, 6. So if I substitute in the point 0, 0, I get x is 0, y is 0. I get 0 is equal to a to the power of b minus 3. That's the exact same as this equation, just substituting in 0, 0. So I'm going to add 3 to both sides. I get a to the power of b is equal to 3. So what you can do here, you might use trial and error to find a and b and see which one works. There's nothing at all wrong with that. If you don't want to use trial and error for a and b, we'll substitute in another point. I'll choose this one, 1, 6. So I'm going to substitute x equals 1, y equals 6 into this equation here. So I get y is equal to a to the power of x plus b minus 3. So I'm going to add 3 to both sides. I get a to the power of b plus 1 is equal to 9. So I can solve for a and b by dividing this equation by this equation. So if I go a to the power of b plus 1 divided by a to the power of b. So remember, the index laws are you keep the same base and subtract the powers. So b plus 1 minus b is just 1. So I get a to the power of 1 is equal to 9 divided by 3, which is 3. So a is equal to 3. And we can easily find what b is. So if a is 3, 3 to the power of what equals 3? Well, of course, that means b is equal to positive 1. So we found a, we found b, and we'd already found c. So the equation is y equals a to the power of x plus b plus c. That's the equation and we're done. Let's move on to some exponential equations. So there are a few types of exponential equations you need to know. So the first that can be solved using algebra by equating powers. The second that it gives an irrational solution and we need our graphics calculator to solve. And the third one involves quadratics. So let's look at this one here. So I'm going to solve it algebraically. The problem is 8 and 4 different bases. What I need to do is I need to write these two expressions so they have the same base. Then I can just equate the powers. So 8 is not a power of 4, but both of them are powers of 2. So I can write 8 to the power of x as 8, which is 2 to the power of 3 to the power of x equals 4 to the power of 2x minus 1.5. So the power to a power rule says you keep the same base and multiply the powers. So this is 2 to the power of 3x is equal to 2 to the power of, now I have to multiply 2 by everything. 2 by 2x and 2 by minus 1.5. So if these two are equal, then obviously their powers must be equal. 3x is equal to 4x minus 3. So you just solve this equation. So remember what you do is you subtract 3x from both sides. So I get 0 equals x minus 3. And of course, that means x is positive 3. So that is the solution here. If you put 8 to the power of 3 in your calculator, you get 512. If you put 4 to the power of 4.5, you get 512 as well. Let's look at this one here. So this one, if we try and do in our head, we're going to be here all day. 50 is not a power of 20, and neither of these are perfect powers. You can't write that as some integer to a power. So this would be difficult. What we do is we use our graphics calculator, and we can do it like this. We can graph this function and this function. What I mean by that, graph y equals 20 to the power of x plus 1, and then y equals 50, and use the calc menu in your graphics calculator to find their point of intersection. So if you do that, the x value of their point of intersection should be about 0.3059. It's an irrational number, so we can't write it as a fraction. So that's the answer got using technology. So let's look at this equation here. It probably doesn't look like a quadratic, but it actually is. Let's let y equal the smaller base to the power of x. See, then 16 to the power of x, well, hopefully you note 16 is 4 squared. So 16 to the power of x is actually equal to y squared. If I square this, I get 16 to the power of x. So what that means is I can rewrite this equation as y squared minus 12y plus 32 is equal to 0. That's why this is a quadratic equation. So now let's solve it as normal. So what we're going to do is we're going to find two numbers that multiply to 32 and add to negative 12. So those two numbers, of course, minus 8 and minus 4. So we have two solutions here. Y equals 8, y equals 4. But remember, y is equal to 4 to the power of x. So we have 4 to the power of x is equal to 8, or 4 to the power of x is equal to 4. So in this case, 4 to the power of x equals 4, x just equals 1. We should be able to tell that off the top of our head. So if I want to solve this, I need to use a trick that I used up here. So 4 to the power of x gives me this. 8 is this. So I have 2x is equal to 3. X is equal to 1.5. So they are the two solutions to this quadratic. Now note, if I did this quadratic and I ended up with something like 4 to the power of x equals a negative, that would have no solutions. Remember, you can't raise a positive number to a power to get a negative. So just keep that in mind when solving quadratics. All right, let's move on to exponential modeling. So for our purposes, an exponential model is just an equation of the form y equals a times b to the power of x. Y and x are the two variables. So a is just the initial value, whatever the y quantity is, this is what it started at, and b is the growth or decay factor. So as we mentioned when we're doing graphs of exponentials, if this number being raised to the power, if it's greater than 1, you go like that, it's an increasing function, so we have growth. And if that number is less than 1, the graph looks like this, and we have decay. The y value is getting smaller as x gets larger. So let's look at this one here. The population of a town, 80,000, decreasing 3% each year. How long before the population will be halved? So first I'm going to come up with an exponential model, which is just an equation linking y, which in this case will be population, and x the number of years. So what we have is y equals the initial amount is a times the growth factor to the power of x. So if it's decreasing by 3% each year, decreasing by 3% is the same as timesing by 0.97. So this is my exponential model, initial value times growth or decay factor to the power of x. So if I want to know when this will be halved, that means I want the population to be 40,000, and I just need to solve this equation here. So what I'm going to do first is I'm going to divide each side by 80,000, and now I have this equation to solve. So this is one of those ones that will yield an irrational answer. So like we did on the previous slide, I'd graph y equals a half, y equals 0.97 to the power of x, and let my graphics calculator calculate the point of intersection. So, using my graphics calculator to do the work, I get x is about 22.76, so it'll take about 23 years to the nearest whole number. Alright, let's try this one here. So I invest money with interest compounded annually, have 30,000 after 5 years, 40,000 after 8 years. What's the interest rate? So here, coming up with the equation is not going to be easy because I don't know the initial value and I don't know the growth or decay factor. That's what I'm trying to find. All I need, though, to find the exponential model, I just need to find A and B. I'm only finding two things. So if I have 2 points, 2 sets of values for x and y, I can find them. So here I have 2 points. If I let x again be the number of years and y equal the amount that I have the point 5 years, $30,000, and also the point 8 years, $40,000. So I can substitute each point into the equation y equals ab to the power of x. So y equals ab to the power of x, and then y equals ab to the power of x. So as I did in a previous example on one of the slides, to find out what A and B are, I'm going to actually divide. So I'm going to take this equation here and divide by this one. So what I get, 40,000 divided by 3 is 30,000, sorry, is just 4 over 3. So that's what I get when I do this divided by this. Now, AB to the power of 8 divided by AB to the power of 5. A divided by A, the A's cancel out. B to the power of 8 divide B to the power of 5, index laws. We keep the same base and subtract the powers. So this is a very easy equation to solve. B will just be the cubed root of 4 over 3. So the answer you get for B is about 1.1. So the growth factor is 1.1. That's an increase of 10% each year. Now, if we wanted to find A, of course, we would just substitute this into, say, this equation here. So A would just be 30,000 divided by B to the power of 5. So A would be about $18,573. So this is the initial amount. It increases by 10% each year. So you'll have $30,000 after 5 years and $40,000 after 8 years. So that's all for indices and exponentials. Let's move on now to sequences and series. So a sequence is just a list of numbers like this, this, or this. So these two first ones have special names. So in this one here, you can see that each term is going up by 3. The way we write that recursively, the next term is equal to the previous term plus 3. This 3 here is called a common difference. The difference between successive terms is 3. 17 minus 14 is 3. 14 minus 11 is 3. 11 minus 8 is 3. So because each term is going up or down by the same amount, we call this an arithmetic sequence. So this sequence over here is not arithmetic because it went up by 5, then by 10, then by 20, and so on. There is not a common difference here. There is, however, a common ratio. You can see each term is double the previous term. So we write that recursively. The next term is equal to 2 times the previous term. So here we have a common ratio. We're multiplying each term by the same amount to get the next term. So in this one, we called it a common difference was 3. Here, the common ratio is 2. And when you have a common ratio, we call that a geometric sequence. If we look at this last one here, well, what's happening, it's not arithmetic because it's not going up by the same amount. We went up by 3, then up by 5, then up by 7. So clearly this is not arithmetic. We're also not multiplying by the same amount. We multiply by 4 to get to this one, then 2.25 to get to that one. Here, there is no common ratio. There is no common difference. We're not adding or subtracting the same thing each time. We're not multiplying or dividing each term by the same number each time. So because of that, this sequence here is an example of a sequence that is neither arithmetic nor geometric. So let's now look at finding the nth term of an arithmetic sequence. So the formula for the nth term of an AP, an arithmetic progression or an arithmetic sequence, Tn equals A plus N minus 1D. So A is just the first term, D is the common difference as we saw on the previous slide, N is just the number of the term you're interested in. So for this example here, what is the 20th term of this sequence? So we have A, the first term's 81, the common difference is actually minus 6 because we're subtracting 6 each time. So to find T20, it's just going to be A plus, so N is 20, N minus 1 is 19 times D. So 81 minus 114 giving us minus 33. So that's easy as to find the nth term when you know A, N, and D. So in this one, we're asked, is 1830 a term of this sequence? So this time, we're actually going to use this formula to find N. So if 1830 was a term of this sequence, which number term would it be? Would it be the 77th term, the 102nd term, whatever? So here, again, we have A is the first term, D is the common difference. This time the common difference is positive because we're going up, we're adding each time. So now we're told 1830, that's the term we're interested in, that's the value of Tn. So using the formula, I have Tn equals A plus N minus 1 times D. So again, I'm looking for, if 1830 were a term of this sequence, which number term would it be? Which number term is N? So I just need to solve this equation. So what I'm going to do is subtract 3 from both sides and just make this easier to work with. So if I divide each side by 7, I get 261 is equal to N minus 1, add 1 to both sides. So because N is a whole number, 1830 is actually a term of this sequence. I've actually just calculated 1830 is the 262nd term of this sequence. How much faster is that than going 31, 38, all the way up to 1830? Now note, if I did not get a whole number for n, if I got like 262.5, then 1830 would not have been a term of this sequence. But because I got a whole number answer, it is a term of this sequence. N equals 262 is the 262nd term. So let's look at this one here. So we need to find T50. So to use this formula to find the value of a term, I need to know A, N, and D. Well, clearly I know N is 50. If I want the 50th term, N is 50. The thing is, I don't know what A and D are. Sometimes what you will need to do is do a little bit of work to find what A and D are. So I'm going to use these two terms to find A and D. If you know two terms in an arithmetic sequence, you can find any other term. So T5 of any arithmetic sequence, T5 is equal to A plus N is 5. So 5 minus 1 is 4, A plus 4D. In any arithmetic sequence, the fifth term is equal to the first term plus 4 times the common difference. So similarly, in any arithmetic sequence, the 14th term is A plus 13D. So A plus 4D, we're told that that is equal to 27, and A plus 13D is equal to 63. I have two simultaneous equations, but don't freak out, these are really easy to solve. So what I'm going to do to solve these two simultaneous equations for A and D is just simply subtract to get rid of the A's. So I go, A minus A is 0, 4D minus 13D gives us negative 9D, 27 minus 63 gives minus 36. So minus 9D is minus 36. We get D is equal to 4. The common difference here is equal to 4. If I substitute D equals 4 into this equation here, I get A plus 16 is 27. A is 11. So I've just found that the first term of this sequence is 11. The common difference is 4. So what would be T50? It would be A plus N minus 1 times D, which is equal to 207. And then we're done. So let's now look at an arithmetic series. So an arithmetic series is just the sum of the terms in an arithmetic sequence. So let's say I wanted to find the sum of all these numbers here. So what I would do is I can very cleverly just take the first term and the last term and divide by 2. Why am I doing that? This gives me the average value of a term in this series. The average, or the middle value, if you like, is going to be these two added up and divided by 2. So if I do that, I get 93.5. See, that is the average value of a term here. Now, what I need to do is I need to multiply this average value by the number of terms. What I need to know is I need to know which term is this. Is it the 20th term or whatever? Now, I know A is equal to 13, and I know that D is equal to 7. So if I want to know which term 174 is, I have Tn equals A plus N minus 1 times D. So what I'm going to do is subtract 13 from both sides and divide each side by 7. Add 1 to both sides and I get 24. This is the 24th term. So to add up all of these terms, all I need to do is multiply this number by the number of terms. So the sum, which I'm going to call the sum of the 24 terms, is 93.5, the average value of the term, times 24. So putting that in my calculator, I get 2244. So what did we do here? Well, what we did was we took the first term and the last term, divided it by 2, and then multiplied by the number of terms. This thing here in brackets, that gives you the average value of the term, and then we multiplied that by the number of terms. The problem is we won't always know the last term. So we can rewrite this last term using the formula on the previous slide. You see, L will be the nth term of this sequence. So I can rewrite this as A plus L is going to be A plus n minus 1D. And then we're all dividing that over 2. So the more common one you'll see, if I just clear this up, it's going to be A plus A is 2A plus n minus 1D. This is the usual formula we use for the sum of the first n terms of an arithmetic series. And if I use this formula, I would have got exactly the same answer. So now we're asked how many terms of this series must be added to get a sum of minus 370. So this time we know the sum, but we need to find n. So the sum, Sn, the sum of the first n terms is given by this formula. So let's just substitute in everything we do know into this formula and find what we don't know. So we clearly have here A is 67, and D, it's going down by 9, so it's negative 9. We know that the sum of the n terms we're interested in is minus 370. So using this formula here, I have Sn is equal to n over 2 times A plus n minus 1 times D. So I need to solve this equation. I'm going to start by making this a little easier to work with. So I've just made what's in the brackets easy to deal with. Now I might get rid of this 2 because, let's face it, who likes having fractions in the equation? So I'm going to multiply each side by 2. So now I get this, and hopefully you'll be able to see that this yields a quadratic. So expanding the brackets here, I get minus 740 is equal to 143n minus 9n squared. So making one side equal to 0, I'm going to get 9n squared minus 143n minus 740 is equal to 0. This is the quadratic I'm going to solve. So to solve this, I'm going to use the quadratic formula. So it's going to be n is minus b plus or minus the square root. So the discriminant in this case is 47089, all divided by 2 times a. So putting that on my calculator, I get n is equal to 20 or minus 4.1 recurring. So we can't have a number of terms that's either negative or not a whole number. So this won't be the answer. We just accept this one. N is 20. What does that mean? I need 20 terms of this sequence to add up to minus 370. So it's a lot of work, but in the end, it's just solving a quadratic. All right, let's look at one more question involving arithmetic series. So here we're told the sum of the first 20 terms is 920, sum of the next 20 terms is 2520. What is the sum of the first 99 terms? So we want to find S99. So that will be equal to n over 2 times 2a plus n minus 1 times d. The problem is we need to know a and d to be able to calculate S99. So what we're going to have to do is use the information we have to find a and d. So let's start by forming an equation here. The sum of the first 20 terms of a sequence is 920. So using our formula, S20, that will be equal to n over 2 times 2a plus n minus 1 times d. So if the sum of the first 20 terms was this, and the next 20 terms is that, what that means is the sum of the first 40 terms is equal to 3,440. So S40 is equal to n over 2 times 2a plus n minus 1 d. So we know that the sum of the first 20 terms here was 920. That's given us one equation with two unknowns, a and d. This has given us another equation with two unknowns, a and d. So now we should be thinking simultaneous equations to find a and d. So let's just make these equations a little easier to work with. So 920, so 20 over 2 is 10. 10 times 2a is just 20a. 10 times 19d gives me that. And similarly for the next one, we have 3,440. This is equal to 20. 20 times 2a, and then 20 times 39d. So we need to solve these two equations simultaneously. So remember, we can only eliminate one of the variables when the coefficient is the same in both equations. So I'm going to times this equation by 2. That will make the a's both have a coefficient of 40. So the top equation becomes this, and I leave the bottom equation alone. So now what I'm going to do is subtract. I'm going to subtract the top equation from the bottom. So 3440 minus 1840 gives me 1600. 780 minus 380d, of course that gives me 400d. Divide by 400, we get d is equal to 4. So we can find a by substituting this into any equation. If I substitute it into here, I get 920 is equal to 20a plus 760. Subtract 760, divide by 20, you get a is 8. So I've just found out this is actually the sequence that starts at 8 and it goes up by 4 each time. So now it's really easy. To find the sum of the first 99, I can now substitute a and d into this equation. I just found that a is 8 and d is 4. So all I need to do is change a to 8 and d to 4 and put this in my calculator. And then I get 20,196 and I'm done. So in all of these questions, we were using that same formula. Sn equals n over 2, 2a plus n minus 1d. Just sometimes you might have to do a little bit of extra work to find a and d first. Sometimes you'll need to use the formula to find n. Let's move on now to the nth term of a geometric sequence. So the formula for the nth term of a geometric progression or geometric sequence is given here, a r to the power of n minus 1. So let's use it on this question here. So what's the 12th term of this sequence here? Well, clearly in this sequence, a is equal to minus 3. That's the first term. Now, r is the common ratio. So if you're not sure what it is, just divide a couple of terms. So the common ratio here is 6 divided by minus 3. It's also minus 12 divided by 6, which is minus 2. So here, the 12th term, T12, n is 12, is equal to a times r. We're substituting a negative, so I'm going to put brackets around it, to the power of n minus 1. So putting that on our calculator, we get 6144. Now we know we've done something right because we got a positive answer. You can see in this sequence, every odd number term is negative, the even number terms are positive. Even number term, positive answer, we know we've done something right. All right, let's look at this question here. So this time, we're going to find T3 in a geometric sequence. We're told T5 and T9. So to use the formula up here, we need to know a, r, and n. Now we know n is 3 if we're finding term 3. But what we don't know is a and r. We need to somehow use the information given here to find a and r. So in any geometric sequence, T5 is equal to a, r. Now, n is 5, so n minus 1 is 4. Similarly, T9 is equal to a, r to the power of 8. In this case, we're told the 5th term was 187.5, and the 9th term was this. So from this, we can find what a and r are. Now this is a very similar trick to what we used on a previous slide when we're doing exponential modeling. We're going to take this equation and divide by this one. So what we're going to do is go a divided by a, well that's just 1, r to the power of 8 divide r to the power of 4. So remember, keep the same base, subtract the powers, and now we're going to go 11.71875 divided by this, and I actually get 1 over 16. So here I have r to the power of 4 is 1 over 16, so r will be the 4th root of 1 over 16. Now here, unlike when we're doing exponential modeling and we knew, amounts would be positive, we have to account that there's a positive and negative solution here. Whenever you're taking the even root of a number, there's a positive and a negative solution. See, in this case, r could actually be the 4th root of 1 over 16, which is a half, or it could be negative a half. So we don't actually know. Now, it doesn't matter which of these we substitute into our equations here. In either case, we get a is equal to 3,000. So we know that a is definitely equal to 3,000, and r is equal to either a half or minus a half. We don't know which one. It won't matter in this case, though, for term 3. So what we're going to have, we have term 1 is equal to 3,000. Because r could be half or negative a half, just so you know, t2 could be 1,500 or negative 1,500. But what will actually happen, t3 will actually be 750. So there's only one possible value for t3, because even if r is minus a half, if r was minus a half, all the odd number terms here would be positive. So we know that this is definitely going to be positive anyway, even though there are 2 possible values for r. And this would come out in the formula as well, because if I substitute it into for t3, I get a times r squared. You get the same number here if you put half squared or if you put negative a half squared. Both of them equal positive 1 over 4. So that's why there's only one possible value for t3, even though there were 2 possible values for r. All right, let's now move on to geometric series. So as with arithmetic series, geometric series is just where you add up all of the terms in a geometric sequence. This is the formula for the sum of the first n terms of a geometric sequence. A times r to the power of n minus 1 over r minus 1. Just a formula, and it includes the same things we've already seen in previous formula. A, the first term, r, the common ratio, and the number of terms. So if I want to find the first 15 terms here, it will just be a times r to the power of n minus 1. Now, what's r in this case? Well, if you don't know, take a term and divide the previous term. Either way, you will get minus 1.5. So this is r. Now I need to put it in brackets because I'm substituting a negative. R to the power of n minus 1, all divided by r minus 1. So putting that in our calculator, we get a decimal answer 702.23. Now we'd expect a decimal answer because these are going to become long decimals quickly. We'd expect a positive answer because the 15th term is going to be the largest term, the most dominant term, and going to be positive. So that's our final answer here. So how many terms are required for the sum of this series to exceed 1,000? So this time, how many terms? We're actually looking for n. We know a is equal to 40. Now r, if you don't know what it is, take any term, divide the previous term. It's actually 1.1. So what we're going to do is we're going to substitute everything we know into this formula to find what we don't know. So the sum of the geometric series here is going to be a times r to the power of n minus 1 over r minus 1. I want this to be greater than 1,000. So let's make this a little easier to work with. So obviously 1.1 minus 1 is just 0.1. So to get rid of what's on the bottom of the fraction, you need to times each side by 0.1. Don't divide it. So then I'm just going to get 40 times 1.1n minus 1 greater than 1,000 times 0.1. Now what I'm going to do is divide each side by 40, add 1 to both sides. So I want 1.1n is greater than 3.5. So if I want to solve for 1.1n equals 3.5, this is one of those exponential equations for which you need technology. I graph y equals 1.1 to the power of x, y equals 3.5 on my graphics calculator, and find the point of intersection. So putting that on my graphics calculator, the solution I get here is that n is approximately 13.14. So what that means is 13 terms won't quite get me to 1,000. 14 terms will get me over 14,000. So I need at least 14 terms of this sum to exceed 1,000. All right, let's go into our final topic now of limiting sums. So let's look at this idea of a limiting sum. See, a geometric series has a limiting sum if r is between -1 and 1. The limiting sum means that you can add infinitely many terms. The sum can keep going and going forever, and it will eventually reach a limit. So let's investigate it in this sequence here. So hopefully you can see that r is equal to -2/3. So clearly, the common ratio here is between -1 and 1. So after this term -8/9, which is -0.8 recurring, the next term would be 16/27, which is 0.59. The next term would be -32/81, which is about 0.395, and so on. What is happening is that each successive term is getting smaller and smaller or closer to 0. So the idea is if I keep adding terms, eventually the terms will become so small they won't really add anything to the sum. So to calculate the limiting sum here, it's a very simple formula. So if this sum went on forever, that's what these dots mean, going forever, it's just equal to a, the first term, over 1 minus r. So putting that on our calculator, we get 9/5 or 1.8. What will happen is if you keep adding term after term after term in this sequence, the sum will get closer and closer to, but never actually hit 1.8. Eventually, the terms are going to become so small they won't add anything to this sum. All right, let's look at this question here. What's the value of x if this is equal to 3/4? So this is clearly a geometric series. A is 1. The common ratio is x. So this sum here goes on forever, infinitely many terms. It will reach a limit only if r is between -1 and 1. The reason is because if the common ratio is between -1 and 1, the terms get closer and closer to 0. So here, we can just use our formula a/1 minus r equals 3/4 to find out what x will be. So we have a/1 minus r is equal to 3/4. So how do we solve this equation? Well, whatever you do to one side, you must do to the other. So we can flip the fraction on the left-hand side as long as we do that on the right-hand side. So we get 1 minus x equals 4/3. So subtracting 1 from both sides and then timesing by -1, we get x is equal to -1/3. So this will be the sequence 1 minus 1/3 plus 1/9 minus 1/27, and so on. If you keep adding terms over and over again to this series, the sum will reach a limit of 3/4 or 0.75. All right, let's now do one more question on limiting sums that is a very hard question. Okay. So here we're told an infinite geometric series has a limiting sum of 12. The sum of the first three terms is 10.5. What is the first term and the common ratio? So we're told the limiting sum is 12. So a over 1 minus r, we don't know what a and r are, but a over 1 minus r must equal 12. So the sum of the first three terms is 10.5. So the first term is a, the second term of any geometric series is a times r, the third term is a times r squared. That is equal to 10.5. So we've got to solve these equations somehow to find what a and r are. So what we can do is rearrange this first equation as I've been doing throughout this entire video. Let's make it easy to work with. Timesing each side by 1 minus r. So what we can do here is substitute that into this equation here. See, this is a times 1 plus r squared. So what I can do in this equation I'm just writing now is replace a with 12 times 1 minus r. So let's use this equation here to solve for what r is. So let's start by dividing each side by 12. So what we get is 1 minus r times this is equal to 10.5 divided by 12. Now what I can do is I can expand these brackets. So I'm going to times 1 by everything in the brackets. And then I'm going to times negative r by everything in the brackets. So this is actually helpful because I can get rid of a few terms. You see, I can get rid of r minus r is 0, r squared minus r squared 0. What I have here, I have 1 minus r cubed is equal to this, and I can solve this really easily. What I'm going to do is I'm going to subtract 1 from both sides, and then I'm going to times each side by minus 1, and then I'm going to take the cubed root. Of course, when you take the cubed root, there is only one solution. So the cubed root of 0.125 is actually 0.5. So I've actually found here that r is equal to 0.5. So substituting that in my equation here, a is equal to 12 multiplied by 1 minus r, which gives me 6. So I'm done. This is actually the sequence 6, 3, 1.5. So you can see the first three terms add to 10.5. The next term will be 0.75 and so on. So if I add infinitely many terms, I get 6 divided by 1 minus a half is equal to 12. So this is the sequence. It has a limiting sum because r is between minus 1 and 1. All right, thank you so much for watching the video. I'm sorry that it was so long. Best of luck for the test. You're a superstar and I believe in you. This has been the luckiest maths teacher in the world. Have a great day.